So what we're going to look at now is we're going to look at vector spaces. And so vector spaces are actually a very mathematical idea, and they can be actually very abstract. But what we're not really going to look so much at them from that perspective here inside of our linear algebra course, but we are going to talk about vector spaces in very general terms, and we'll talk about the properties of vector spaces. And then I'm also going to utilize this opportunity to talk about some specific cases that we will be seeing a lot of, so that maybe you can kind of generalize your thinking for all the different kinds of vector spaces that we'll be looking at. We are going to be looking at several of them. And so, what you want to be able to do is generalize what it is that we're doing here with like R2 and with R3 and with the polynomials out to any vector space that you're looking at. Okay. So, let's start out with a definition here. And so a vector space is a non-empty set, call it V, combined with another set F, which is, it's called a field, but we don't really need to get into that too much. And then it has an addition operation and a scalar multiplication operation, all right? And we're going to multiply by members of F. And it's an operation and it has, with those operations, right? Scalar multiplication and addition. So let's take a look at an example of a vector space, and I'm going to show that it is in fact a vector space, okay? Pardon me, this statement with the following operations means that there are some characteristics, and there are 10 of them, and that we're going to go over them in just a moment. So let's first talk about R2. And R2 is the set of all vectors made of what we call duples. Okay, and so let's say, for example, I have a vector V. I have a vector V, okay? And if the vector V is in the R2 if it is made up of, and we'll call it little v1 and little v2, okay? That is that there are two values, okay, in the vector. Both v1 and v2 are real numbers. So v, okay, belongs to, and that's what that means, belongs to R2, okay? Example here, let's say, for example, v equals, and I'm going to write them mostly now as column vectors, 1, 1, there's a column vector, okay? We might also have w, which is another vector in v, we'll say, and that'll be 0, 1. And we might have another vector, call it u, which equals, let's say, negative 1, 2. Okay? Weird. Now, when we talk about the geometry on R2, okay, generally what we're thinking about is we're thinking about working on the Cartesian plane, okay? And the thing is that R2 is represented by the Cartesian plane, but it isn't the Cartesian plane, all right? The two aren't exactly the same thing, right? What it means is that we utilize the Cartesian plane in order to kind of show R2, okay, and to talk about geometry using R2. But the two actually are not exactly the same, and you're going to see why that's the case when we start talking about subspaces. So like, for example, 1, 1 here is this vector right here, okay? What we do, the vector is represented by going over 1, up 1, and then we'll draw it, okay? We're going to draw it from the origin, all right? Now, it turns out that in other instances, say for example inside of physics, you've seen inside of calculus, where what you've been doing is the vector can be, the vector 1, 1 can be anywhere in the plane. Well, we're going to allow that too, and especially when we do addition, but in general, we're going to anchor our vectors at 0, 0. Okay, so in general, we're going to anchor at 0, 0. So like this one here is V, okay? Let's say, for example, we have W, okay? W was 0, 1, so here's W, okay? And U was negative 1, 2, okay? Let's actually make it negative 1, negative 2, make it a little bit easier to see. Negative 1, negative 2, okay? Okay. Which is this vector right here, okay? So you'll utilize each value, okay? So this is basically your x value. This one will be your y value, the one below. Top x, bottom y, when we talk about the geometry on R2. Now, when we get beyond 3 dimensions, it doesn't make sense to talk about them as x, y, and z. What we'll talk about them as x1, x2, x3, x4, and that just means which row are they located in. Okay, so like which row are located in? X1 is located in the first row, X2 is located in the second row, X3 is located in the third row. But when we actually do have a geometric representation, we can call them the x value, the y value, the z value inside of the vector. Okay? Just to make it very clear, you are going to see 2 different ways that I'll do vectors. One is this arrow way, and the other one is with bolding. All right. Okay. Now, the next thing that we have is closure under addition, right? So this is the first property of vector spaces, all right? So this states basically if U and V belong to V, then U plus V, okay, my vectors U plus V also belongs to V, okay? So like, let's take for example, we'll let U equal 1, 1, and V equal -2, 1. Okay. When I add the two of them together, U plus V equals 1, 1 plus -2, 1, which equals -1, 2. Okay. Since -1 and -2 and 2, excuse me, belong to the reals, belong to R, the resultant vector U plus V also belongs to R2, right? So basically, any vector, right, any duple where the two values are in the real number line, okay, they are going to be part of R2. And so what you notice is that if you add 1, 1 plus -2, 1, you get another one that has real number values, right? And then there are 2 of them, right? So it also belongs to R2. And so hence we're like, oh, the addition of U and V belongs to R2. Now, let's talk about it more generally, because that's only for 2 specific vectors. How do I know it's the case for all vectors in V? Well, what we'll do is we'll just say, here's our little proof for R2. We're going to let V and W belong to R2, okay? Thus, V will let V equal V1, V2, and we'll let W equal W1, W2, okay? V plus W will then equal V1, V2 plus W1, W2. Okay? This equals, and we could just write this out as V1 plus W1 and V2 plus W2. All right? Now, here's the thing, and this is just the statement that you might want to make, right? Because addition of real numbers gives me a real number, produces real numbers, V plus W belongs to R2. Just move myself up here a little bit. There you go. That's better. Belong to R2. Okay, so V1 plus W1 belongs to R2. V2 plus W2 belongs to R2. Belongs to R. Both of these guys belong to R, so we have a duple, 2 values, right? Okay, made up of values in the real number line, and so consequently, we have a vector that's in R2. And this is generalized because what we did was we picked any 2 vectors V and W. I didn't specify what V1 and V2 were, and I didn't specify what W1 and W2 were, And so consequently, when I added them together, you can assume that this is true for all values of all vectors inside of the space, okay? Because they're what's called generalized vectors, okay? All right, now let's take a look at the geometry. Okay. Now the geometry of vectors, okay, is, or the geometry of vectors in R is what we call tip to tail, okay, tip to tail. And so when we add two vectors, right, like let's say for example, with like v equal 3, -1, and we're going to let w equal 2, 2. All right, great. That's good. So now if I take v, okay, I got 1, 2, 3, 4, 1, 2, 3, down 1, okay, there's v. All right, okay. And then what I'm going to do now is I'm going to add, I'm going to go up 2 over 2, right, okay, from the end of v. So here's v, okay, and then I added w to it, tip to tail. So this vector, this resulting vector, we'll make it a special color, we'll make it red. This resulting vector is the addition of my two vectors, okay? And what we can see is that's 1, 2, 3, 4, 5, 1, okay? 5, 1, right? And this one here, that is called v plus w. And I'll leave it to you to notice that 3 plus 2 is 5, -1 plus 2 is 1, and so hence we actually have that addition. All right, so we've got that idea of the tip to tail addition. This is going to work with any set of vectors in R, okay? Even if you could like imagine it in R6 or R7 where we have 7-dimensional or 10-dimensional or whatever dimensional vectors, it's still at least conceptualized as the addition of vectors. So we don't have to actually kind of think about it any other way. We're going to think it's the tip to tail method for adding two vectors together. All right. The next one here, next big one, biggie here, is called closed under scalar multiplication. All right. So this is if v belongs to v, okay, and S belongs to my field F, okay, then SV, right, the scalar multiplication of S by V is going to belong to V, all right? So basically what that's saying is that if I take a scalar multiple of a value, then that value is going to continue to belong to V, all right? So for example, I take let S equal 2 and V equal -1, 3, all right? Then SV equals 2 times -1, 3, okay, which equals -2, 6. Okay, and so that is, in fact, our, excuse me, that's our resulting vector. Now, if I want to be generalized, if I want a proof of closure under scalar multiplication, for R2, I'll do something similar, right? What I'll do is I'll let S belong to R. So the field that R2 is closed under is R. So all of our scalars are real numbered values. So let S belong to R and V belong to R2. Okay. We'll let V then equal, and we'll just generalize, call it V1, V2, right? So SV equals S times V1, V2, which equals SV1, SV2. Right? Now, this is just a real number times a real number. SV1, okay, and SV2 belong to the reals, okay? That's because a real number times a real number is just going to give you another real number, okay? So SV belongs to R2. right? Once again, I've got duples, right? Two of them, and both of them are real numbered values. So R2 is closed under scalar multiplication. Cool. Now let's talk about scalar multiplication from a geometric perspective, right? When we talk about the geometry of scalar multiplication, what we're talking about is we're talking about that we're going to be shrinking or stretching a vector. So this, let's say, for example, we take our vector 3, 1. Okay, that's V. And S will equal, let's like it equal 2. So we'll double it. Okay, so SV is going to equal 6, 2. So we'll start with 3, 1, 1, 2, 3, 1. Okay. And then we're going to go out to 6, 2. 1, 2, 3, 4, 5, 6, up 2. What I want you to notice is that there's no change in that direction of the vector. Okay, the vector is still in the same exact direction. All that's happened is that it's stretched it. Okay, so it stretched it by doubling it, essentially. Okay, let's suppose that what we do instead, okay, is we say, okay, well, let's, pardon me, this is V, this is 2V. Let's take a different one. We'll take W. We'll let W equal 3, 3. Let's let W equal, let's have it be 3, negative 2. Great. Okay. And then, pardon me, choose another vector. Let's let it be 6, negative 2. And then let's let S equal 1/2 now. Now what we expect to have happen here is that we're going to shrink the size of the vector. No change to the direction of the vector. The vector will remain along the same line, okay? But what we'll do is we'll actually stretch it. I mean, excuse me, shrink it this time. So 6, negative 2, that's 1, 1, 2, 3, 4, 5, 6, and then negative 2. So there's that. Okay, and SV is going to thus equal 3, negative 1. Okay, so there's that. 1, 1, 2, 3, down 1. Okay, great. And so what we've done is we've effectively shrunk it in half by multiplying it by 1/2. Okay, so geometrically, we should state and notice, okay, that geometrically there's no change to the direction of the vector. Only its length. All right, that plays out in our two examples right here, right? So when I stretched this one by 2, I doubled its size. When I shrunk this one by 1/2, I shrunk it in half, utilizing first the scalar 2, and then secondly the scalar 1/2. Okay, now let's talk about commutativity of addition. Okay, pretty simply stated that when we're multiplying vectors, we have to make sure that we in fact have commutativity of addition. Okay, that is that if you take the vector u plus the vector v, it equals v plus u. And so in R2, this makes a lot of sense. All right, I'll show you exactly what this looks like. Okay, all right, we'll let v, right, okay, equal, we'll have v1, v2. All right, and u equal u1, u2. So u plus v, okay, is going to equal v u1 plus v1 and u2 plus v2. Well, what you want to notice here is in fact that we could switch them because in the real numbers we do have commutativity of addition. So v1 plus u1 is going to equal the same thing as u1 plus v1. It is. It always is. That's how you add real numbers. Okay? And u2 plus v2, that's also, that's commutativity when we add real numbers. We can add real numbers in any direction we want. And so that means that this then is, right, pardon me, this gives me then v1, v2 plus u1, u2. Okay? Which is v plus u. And so we notice that we actually are commutative. Okay? And so, things like that, they happen all the time when we were working in linear algebra. For those of you who are going to end up studying math, this is actually going to become really handy that you kind of go, oh, okay, so I don't really want to talk about like the individual vectors. I want to talk about the components within the vectors. And so I'm just kind of showing you this one for that reason with the reals. Works with all of them. And if you don't have this actually working, then you don't have a vector space. All right. We're not going to get too deep into that. But again, like if you go into, an upper division abstract algebra class or into an upper division linear algebra class, that's one of those things where they're like, wait. This one doesn't have commutativity of addition. What happens then? Oh, well, not a vector space. But R2 is a vector space. And it turns out in this class, we're pretty much going to work solely with vector spaces, except in sections 4.2 and 4.3. Okay? All right. Now, a geometric example for commutativity of addition is basically that we can add tip to tail two vectors any way that we want to. Okay? So, let's take first, we'll let v, okay, equal, and it'll be 1, 2, and u equal to, let's have it be 3, -1. Okay? Now, adding it addition-wise, no problem. I mean, you can kind of see -1 plus 3 is 3 plus -1. Great. 2 plus -1 is -1 plus 2. Those two are equal. Good. What we want to do is we want to understand that with vectors, it doesn't matter which tail, right? Okay, which which tail we're adding to which tip, right? That's basically kind of the idea, I guess. So let's take red. All right, and that's -1, 2. So -1, 2. Okay. And then we will take 3, -1. 1, 2, 3, -1. Okay. So if I do v plus u, okay, so there's those two. Okay. There's our two actual vectors. All right. Well, let's say, for example, I take first, I'll do u plus v. Okay. U plus v will look like this. We go out to the end of u, and then we're going to add v, so that's going to be -1 and up 2. Okay, so it's going to go here. Okay. On the other hand, v plus u, other direction, is going to start up here, okay, at the end of v, and then we'll go over 3, 1, 2, 3, and we'll go down 1. And there you go. That's some commutativity. All right. We end up at the same place no matter which way we go. Let's actually construct that resulting vector. We end up here. No matter which direction that we go in from a geometric perspective, we're going to end up at the same place or the same location. And so consequently, that's what we talk about geometrically when we talk about the commutativity of addition. All right. Simply stated, you can add your vectors in any direction that you want to. All right. It's just the geometry also works. Okay. So this one here is u plus u plus v, which equals v plus u. All right. And what you'll notice is that you can actually generate kind of a parallelogram. Okay. So notice you generate a parallelogram. This is going to end up becoming kind of handy. the next idea we want to deal with here is associativity of addition. All right. I'm not going to get too deep into this. I'm not going to talk about its geometry either. But basically what that means is that if you could add a pair of vectors first and then add a third vector, it's the same as adding the last two vectors first and then adding the third vector onto it. All right. And I won't get into that into the proof. It's just something you should know. We do have associativity when we look at R2. R2 is a vector space, and so we'll end up with our associativity out of it. All right. This is the zero vector. Now, the zero vector is kind of a very powerful idea. We've already seen it quite a bit already when we deal with homogeneous systems. But also, we want to talk about the zero vector from the perspective of the geometry of the zero vector. Okay. So first, in R2, the zero vector exists. So 0 belongs to the reals, right? So we'll call it V equal to 0, 0, right? Belongs to R2, okay? And we call this the zero vector, right? So we'll put 0 with a little vector line over it, and that's called the zero vector, versus calling it 0, or talking about the zero matrix, okay? So this is the zero vector. Some things about the zero vector, I mean, it's already played a big role. Okay, we've seen it quite a lot. It will continue to play a very big role. If a vector space, if a set does not have the zero vector, it is not a vector space. So here's the thing, right? Okay, we could imagine, well, one, okay, first, R2's got it because it's right there. There's the zero vector. All right. It has no length, no direction. Or it has zero length, which should say it has zero length and no direction. So it is not in any particular direction. When we add the zero vector to any vector, we end up with just that vector. It's an additive identity. What's what we call an additive identity. So we'll talk about it. That's a special property. Right? Special property. Okay, is that take V plus the zero vector, we get V. Okay. In addition to that, if we take S, some scalar belonging to F, SV just equals the zero, not SV, S0. S0 just equals the zero vector back. Okay. All right. So from an addition standpoint and scalar multiplication standpoint, we just get 0 back whenever we multiply by the zero vector. And if we add a vector plus the zero vector, we get the zero vector back. Okay. And there we are. And that's the zero vector. You must have the zero vector inside of a space in order for it to be a vector space. There it is. Okay. Now, if, okay. Now, here's this idea of the existence of an additive inverse. If V, right, belongs to the vector space V, then there exists a vector, call it negative V, such that V plus negative V equals the zero vector. Okay? All right. So if you kind of think about this, the way this kind of works is it's basically saying, well, I know that I should be able, if I add any two vectors together, right, I get another vector that's inside of the space. That's closure under scalar multiplication, scalar addition. In addition to that, I also have the zero vector, right, because I established that the zero vector was in there. So what vector do I add to V, right, to get back to the zero vector, all right? And that is this inverse idea, okay? So in R2, if, say, for example, V equals like -1, 2, then negative V is going to equal 1, negative 2. And for R2, it's simple to see that this is equal to, okay, negative 1 times V. And since negative 1 belongs to the reals, we know that negative 1V is actually also going to belong to the real numbers as well. Okay, so what that basically means is that it's going to allow us, that vector, okay, it's going to allow us to, equal to 0, right? When we add it to one vector plus its inverse, additive inverse is going to end up equaling 0. There we go. Okay. Now, from a geometric standpoint, what this means, okay, and it ends up becoming a kind of a powerful idea. We're going to see it quite a lot. Is this idea that if I say go out on one vector, if I move out on one vector, right? So let's say, for example, that V equals 1, 3. Okay. Then negative V is going to equal negative 1, negative 3. Okay. Now, 1, 3, V, 1, 3, it's going to be right here. Here's V. And then negative V is going to go down negative 1, negative 3. Excuse me. Now, if I had drawn that better, you could see very clearly that they're in opposite directions. All right. So multiplication by negative 1 reverses the direction of a vector. It basically, what it does is it's going to reflect it over y equals x. Okay, right? And then what we can see is that if we add them together, so v1 plus v2, okay, v1, right, or v plus v minus v, excuse me, v minus v, v plus negative v, you're going to go out to the end of v, and then we basically switch directions, and we go back the other direction, okay? So this thing, it ends up back at 0, so this ends up being v plus negative v, right? So you go out on the one vector, and you come back on its negative, all right? So there are two things, right? So we can addition of additive inverses moves out on one vector and back on the other. So now we've got four more properties of vector spaces. The shorter ones, they are important from the perspective of like doing operations and the like. They don't really have the same kind of geometric relationships as some of the other ones, so I'm going to kind of go over them a little quickly. They basically all flow through, and if we were doing more proof work with this, you'd see that each one of these kind of just flows from earlier proofs. Okay, the first one's the unit property. If V belongs to V, okay, there exists a value, call it 1, call it a multiplicative identity, all right, value 1, such that 1 times V just equals V, right? So there's some way, there's some scalar that we can multiply by V by in order to get V back. In the case of the real numbers, it's 1. Yeah, go figure that out, okay? Associativity of scalar multiplication, all right? So if R and S belong to that field F that all of our scalars belong to, and V belongs to V, okay, then RSV equals RSV, okay? So if you multiply your scalars first and then multiply by the vector V, you will still end up with the same thing as if you multiplied one scalar times V and then multiplied by another scalar. So essentially, right, you can kind of do those operations, not necessarily in any order that you want, although they can. But basically, it doesn't matter which one you multiply the vector by first, you still end up with the same values. All right. Then we have the distributive property of scalar multiplication over vector addition. All right. That is, if R belongs to F and V and say W belong to V, then R times V plus W equals, and our scalar just distributes, RV plus RW. Okay. There we are. And then finally, the distributive property of scalar multiplication over scalar addition is R plus S. So if we add, if R and S are part of our field and V belongs to the vector space V, then R plus S, now scalar, when we add scalars and we multiply them by V, it's the same thing as saying R times V plus S times V. Basically, it's the same as multiplying by the scalar first and then adding. Okay, and that's the scalar multiplication over scalar addition. Okay, and what we want to know is we just want to notice and understand that this happens. That we can do this, that we're allowed. Okay, and what that'll allow us to do, and we'll see this in a little bit, is it'll allow us to kind of like break up our vectors, right? It'll allow us to break up our vectors into linear combinations, or what we call linear combinations, and it'll allow us to manipulate them in ways that we couldn't think about otherwise, okay, but that end up being very handy for us drawing conclusions about vector spaces, okay? So what we've gone over is we've essentially gone over what makes something a vector space. These are the properties of a vector space, and we've gone over a very specific example called R2, okay? So R2 isn't the only vector space, but it is a vector space that we're going to use a lot of, okay? So you want to understand how R2 works and how the geometry on R2 works too, all right? And this concludes the lesson.